Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In today's class, we will discuss about a particular property of the system that we have ignored so far. For example, in all our previous discussion, we have defined the state of the system as a function of coordinates, but what we have ignored is its time dependence. But from our classical experience, from the experience that we have from this classical world, we see that the system actually evolves or changes with the time. How do we incorporate that aspect into our quantum mechanical systems? That is the topic of our discussion today. So, in this context, we will be discussing the time dependent Schroedinger equation and its consequence on different systems. First, we would start from the fact that if you remember, we said that for a quantum mechanical system, the state function contains all the information about the system that we can possibly want to know. This state function depends of course on the spatial coordinates x, but it also has got its temporal dependence. That means, this function, the wave function of the system is a function of time as well. We also discussed while discussing the postulates that while the wave function itself does not have a meaning, what has a meaning is the square of the wave function or the psi star psi, which has a probabilistic meaning. Now, if you compare this system with classical mechanical system, for example, using Newton's equation of motion, we can always tell that if we know the initial position and velocity of a particle using classical mechanics and Newton's equations of motion in particular, we can describe the position and momentum of this particle in any future time. So, the time dependence of the system is easily obtained through classical mechanical treatment. But in quantum mechanics, how do we say that how does this wave function evolve in time, or how does this probability density evolve in time? What is the time evolution of different properties of the system? This is what we are going to discuss in today's class. Now, before doing that, let us see what are the sources of time dependence in our system. There could be two possible cases. One where the operator itself is time dependent. That means, when we write down the quantum mechanical operator, time appears explicitly. That means, if I consider it, if I try to give you an example, for example, if I apply a potential energy where the potential energy would actually keep changing as time progresses. So, in that case, the potential energy has an explicit dependence on time. When the operator itself is time dependent, in that case of course, we have to worry about how the system evolves in time. But what we have seen so far, we have solved quite a few systems. If you recall, none of the quantum mechanical systems that we experienced or we treated had explicit time dependence in their operator. It is to a great extent true that many of the operators that we will be dealing with in quantum mechanics and its application in chemistry, we would not see many examples of operators where operator has explicit time dependence. But of course, this is a straightforward case. If the operator is time dependent, so we must be concerned about the time dependence of the wave function. But even when the operator is not exclusively time dependent, then also we may have to worry about the time dependence of the system. For example, we know that Hamiltonian operator has a kinetic energy contribution, has a potential energy contribution. Let us consider a molecule and write down its Hamiltonian. So, suppose we have the Hamiltonian of the molecule, and for this Hamiltonian, suppose we say that we solve the Schrodinger equation and we obtain this the value of psi, the eigenfunction, and the value of E, the eigenvalues. The energy and the wave function is known about for that system. This is the initially prepared molecule. Let us call this molecule as M. Now, suppose suddenly I interacted this molecule with external field. Let us say I irradiate this molecule with light, or I ionize this photoionize this molecule. So, when I do that, so suppose I am photoionizing this molecule, what I have is that a cation plus a free electron. So, the free electron goes out and what I have is a cationic system. Now, this cationic system has one electron less compared to the molecular system. So, therefore, its Hamiltonian has changed. So, suppose I call this Hamiltonian as H prime, which is a different Hamiltonian starting from this original Hamiltonian. Now, when I have changed I have done this photoionization, the electron is gone. Now, the molecule is suddenly finding itself as a cationic species. Now, what happens to the wave function? So, the initial wave function that we had was an eigenfunction of this Hamiltonian, the original molecular Hamiltonian, but this function is no longer an eigenfunction of this changed Hamiltonian, because this changed Hamiltonian corresponds to a cationic system. So, the wave function or the state of the system will slowly change to another value psi prime, which may be an eigenfunction of this M plus or the cationic species. But we did this photoionization suddenly, but the system or the molecule would evolve in time to come from psi to psi prime. So, here even when my Hamiltonian itself does not have an explicit time dependence, still the wave function changes with the time. So, there can be a time dependence of the wave function even when I am considering a Hamiltonian or an operator to be more general, when I am considering an operator or a Hamiltonian which does not have explicit dependence of time. Our discussion is mostly on systems like this, where operators do not have explicit time dependence, and we would see how the properties of the system would change in time. To do this, we would actually introduce a new equation. This equation, when you see, you know that this is Schroedinger equation, but this is a time independent version of Schroedinger equation. We have a time dependent version of Schroedinger equation, which is given as H psi equals I h bar where this is the left hand side is the operation of Hamiltonian on the wave function, and the right hand side you see is I h bar d psi by dt. So, this equation, the time dependent Schroedinger equation, is a first order differential equation with respect to time. So, this we would treat as a postulate of our quantum mechanics, that when we have system where the Hamiltonian does not have explicit time dependence, this time dependent Schroedinger equation is followed. So, this is our time dependent Schroedinger equation that we have. Now, the point is this psi, as you can see, this psi will have explicit position and time dependence. I would like to write this in as again a variable separation of variable, that let this total wave function be a product of psi x, the function which has only space dependence, and another function, let us call that f, which has explicit time dependence. So, now this kind of wave functions, the eigenfunctions which depended only on space, we have seen in plenty of examples. For example, particle in a box, particle in a sphere, hydrogen atom, harmonic oscillators. In all these cases, we saw the Hamiltonian did not have any explicit time dependence, and the wave functions that we didn't obtain also did not have any time dependence. So, this part of the wave function we already know, and now something new is appearing over here, which is the time function. Now, let us apply this new definition of the function in time dependent Schrodinger equation. So, when I do this, I have equals I h bar, I have a time derivative of the wave function, and I see I have a function which has one part has exclusive space dependence, another has exclusive time dependence. So, the part that has exclusive space dependence would be independent. So, therefore, so in this case this time derivative could also be written as partial derivative, especially because we have the space dependence also. Now, look at the left hand side. The Hamiltonian does not have, the Hamiltonian has kinetic energy term, potential energy term. So, we are aware of this, but it does not have any explicit time dependence. So, therefore, no matter what functional form has this Hamiltonian, it would only be having some effect on psi of x, in particular if the Hamiltonian has a differential operator, it will be differentiation with respect to x. So, therefore, the f function will be we can bring it out of the purview of Hamiltonian. So, we write this now. Let us divide both left hand side and right hand side by this psi x of t, that means psi x multiplied by f of t. So, when I do this, in the left hand side I have this term, and in the right hand side I have where I have from this step to this step, I came by dividing psi x f of t in both left hand side and right hand side. Now, you see I have some terms in the left hand side of the equation, some in the right hand side equation. The terms in the left hand side have dependence only on space or x dependent, and in the right hand side I see functions which have only dependence on t. So, left hand side has x dependence, right hand side have t dependence, and both are equal. In such a case, we can say that both left hand side and right hand side are equal to each other, but they are also both constants, because both the sides depend on two independent variables and they are equal. So, this can happen only when both left hand side and right hand side are equal to constant, and let us give this constant a name E. You would soon realize why I gave this constant name E, because when you look at this left hand side, you see when I rearrange this equation, I get h psi divided by psi of x is equals to E. So, therefore, when I rearrange this, I get this equation is something very familiar to us. This is simply the time independent Schrodinger equation. So, what we see is that we started from time dependent Schrodinger equation, we used this variable separation, saying that let the total wave function have a spatial component and a temporal component. In that, when we do this, we arrive at the time independent Schrodinger equation. So, therefore, the time dependent Schrodinger equation is more general. We can derive the time independent Schrodinger equation from this time dependent Schrodinger equation. So, this part we know, and we also know about this E. What are they? They are the eigenvalues of where the psi are the eigenfunctions of this Hamiltonian. So, for example, since Hamiltonian is a Hermitian operator, I would always know that I can write such a equation where n represents one of the many eigenfunctions of this Hermitian operator, because Hermitian operator will have a complete set of orthonormal eigenfunctions. So, this psi n is one such eigenfunction corresponding to the energy E n. So, I can write many such equations, psi 1, psi 2, psi 3, for each of them I can write this Schrodinger equation. Now, let us look at the right hand side of this term, which is something new that we would obtain. When you look at the right hand side, you see I have this kind of term. I will take this I h bar to the right hand side, now I integrate both left hand side and right hand side, but before that let us look at this. What is E? E is, we can express E as h bar omega. You have seen that h bar is an universal constant, and we express this in terms of this angular frequency as E is h bar divided by omega. So, therefore, E by h bar is simply minus I omega dt. Now, I integrate both left hand side and right hand side. When I do that, you would see that left hand side will give me a natural logarithmic function, and the right hand side will give me minus I omega t plus a constant of integration, and therefore, f of t would be some constant multiplied by E minus I omega t. So, now we see that this f, the time dependent part of the function, has a simple form as some constant multiplied by e to the power minus I omega t. So, how is this omega defined? Omega is defined in terms of E. What is this E? I look at this left hand side of the equation, and then I see that this E is one of these eigenvalues of this time independent Hamiltonian. So, therefore, I can write this, for example, for a given value of E n, I can write this function as E. So, in other words, my psi, the total wave function, I can write as, when I am writing this, the wave function as both time and space dependent, I would write the capital psi, which is given as 2 bars over here, and only when I have spatial dependence, the wave function would be written as small case psi. So, I have now psi x multiplied by e to the power minus I omega n t. So, this is what I get as a general form of this time dependent wave function, when one important thing, when the Hamiltonian does not have explicit dependence on time. So, I have this second term is called a time factor. Now, we would see something interesting from this. So, we found that our psi of x t is given as psi n x e to the power minus I omega n t. So, I can write this as psi n. So, this is one of those for time dependent functions. Now, let us look at what is the probability density for this time dependent state. So, the probability density for this time dependent state would turn out to be, if I take the absolute square, you would see the psi n. So, I will get psi n star psi n. So, which will be absolute value of this, and then multiplied by this function multiplied with its complex conjugate. So, when I look at this function, this is an exponential function. So, its complex conjugate will be simply e to the power plus I omega n t, and when I multiply them, this becomes 1. So, therefore, what I see is that although this function, the total time dependent function, has a time factor in it, but what I am seeing, what I am observing is that the probability density is independent of time. So, the probability density does not have time dependence. So, the probability density remains the same no matter how the time changes. When such a case happens, such a situation arises, we call this function as a stationary state. Please note, stationary normally means which is not moving, which is at rest, but here the system is not necessarily at rest. What it means is its probability density does not change. For example, if you take particle in a box problem, you saw that if I am looking at the second or third wave function, I observe a point where I have a node, or I observe a point where I have the maximum probability. So, what this analysis tells, that the place where I am observing a node will remain so no matter how long I wait. The place where I observe maximum probability will still be the place of maximum probability even as time passes by. So, therefore, that state, the eigenfunction of a time independent Hamiltonian, is a stationary state, because there the probability density does not change with time. We can also say that, for example, the expectation value of this Hamiltonian operator, if I have to consider. So, I would simply do that as where I am integrating over all space all time. In that case also this expectation value or the average value will be independent of time, because you see the psi n star and psi n will have the time dependent, that time factor would simply become 1, and therefore, the expectation value will also become independent of time. So, both average value as well as the probability density would not change, and in that case we call this system as a stationary state. Now, we will look at another case where the state would become non-stationary. Let us come to that. Suppose in the previous example we said that the psi n, which is the state of the system, happens to be an eigenfunction of this time independent Hamiltonian. But suppose I say the psi of the state of the system is actually not an eigenfunction of the time independent Hamiltonian. So, that means the state function is not an eigenfunction, rather it is any other arbitrary function. When this is the case, what I can do is that I can express, because the psi n's are the eigenfunction of a Hermitian operator which form a complete set of orthonormal of eigenfunction set. So, therefore, I can express any arbitrary function which is not an eigenfunction, any arbitrary function as a linear combination of the eigenfunctions of the time independent Hamiltonian. So, I write this as C n psi n x, and for each case I use this time factor as this. So, I am expressing this total state of the function, which is now not an eigenfunction of the Hamiltonian. So, therefore, I am expressing it as a linear combination of several eigenfunctions. So, to make it simple, we will consider the case where the linear combination has only 2 terms. So, C 1 and C 2, and in that case, if I have to obtain this psi star psi, you would see that I will get, instead of doing this, I am writing this down. So, I would get these 2 terms which will not have it. So, you can just express this as a 2 term C 1 psi 1 e to the power minus I omega t, and plus C 2 psi 2 e to the power minus I omega 2 t, and then when you obtain this you would get this. So, I would get another term C 1 star psi 1 C 2 psi 1 star psi 2 e to the power I omega 1 minus omega 2 multiplied by t, plus another term which will be C 1 C 2 star psi 1 x psi 2 star e to the power I omega 2 minus omega 1 multiplied by t. So, now when I look at the probability density of this function, which is not an eigenfunction of the Hamiltonian, in that case I see that it will have some time independent terms, plus I have these terms which have explicit time dependence. So, now I see the probability density is dependent on the time. So, this time factor still survives. So, that means it will say that the probability density will keep changing with time. And when is that happening? That is happening when my state function is not an eigenfunction of the original Hamiltonian, rather it is a, I am expressing it as a linear combination of several eigenfunctions. So, it is an arbitrary function which is not an eigenfunction. In this case, where the probability density has explicit time dependence, I call them as non-stationary states. So, these are non-stationary states. So, that means their probability density would keep changing with time. So, we discussed about the stationary state and the non-stationary state. What is now interesting is that to look at that we have these C n terms, but we still do not know what this C n, because the moment if we find out what is C n, then we can easily find out what is the time evolution of this probability density, because all other quantities are known to me. Psi 1, psi 2 are known, because I assume that I have solved the time independent Schrodinger equation. Omega 1, omega 2 are also known, because they are closely related to E 1 and E 2 and its solutions are known. So, what is not known is the C 1 and C 2. So, we will now look at how we can obtain this C 1 and C 2. So, to obtain my C n, suppose I want to I want to obtain my C n. What I would do is that I will do a little exercise. I saw that stationary states probability density did not change with time, but then there are non-stationary states where the probability density has explicit dependence on time, but to be able to do that we need to know these coefficients C 1 and C 2 and so on, which are actually the coefficients that we used for the to express the state of the system as a linear combination of the eigenfunction of the time independent Hamiltonian. How we get these coefficients and what are their consequences are what we will discuss in our next class. Thank you for your attention.